So let's consider sampling from a large population of people who on average get the recommended amount of sleep each night, 8 hours a night. So some people sleep more and some people sleep less, but the population average is 8 hours. Would we expect each sample of size 30 to have a mean of exactly 8 hours? So hopefully you know that no, we wouldn't because of sampling variability, but we want to think about what values the sample mean would take. So coming back to that idea of sampling distributions again. So first I wanted to point out that in this exercise, we're assuming that we know the population. So this would actually be unusual in the real world, right? Usually we don't have the whole population, we only have a sample. But it's going to be helpful here to pretend we know the population to see what values of the sample would occur. So notice we're given some values, the mean and the standard deviation, that summarize the population. And numerical values that summarize the population are called parameters. It's also good to think about what we're looking at in this distribution. So if we think about this histogram as being made up of a bunch of dots, you can't really see them all here, but each dot in this distribution is one person's sleep time. Right, so we're looking at a distribution of a bunch of different sleep times for different people. So again, the average is 8, and the standard deviation, we would interpret that in terms of individual people. So to interpret the standard deviation, we would say on average, a person's sleep time is, let's see, the standard deviation is 1.51 hours from the mean sleep time, which in this case is 8. So the standard deviation describes the typical distance from one person's sleep time to the population mean. So we're going to imagine repeatedly taking samples of size 30 from this population, and we're going to use another applet to do that. So we're going to start on this main ISI applet page, but instead of choosing one proportion like we were doing in Chapter 1, this time we're going to choose one mean. So you can see the population there. If I click Show Sampling Options, I can change my sample size. I want a sample size of 30. And if you draw samples, you can see the blue dots here are the points from the population, the people from the population that have been randomly sampled. And then those 30 people's sleep times are being shown in this next graph here. So in this particular sample of 30, the mean is 8.1 and the standard deviation is 1.646. Because this is just one of many possible samples, right? Every random sample of size 30 is going to be a little bit different, and I've just copied one of them into your notes. So this is one sample of size 30. In the applet, we saw a different one. So again, in this distribution, each dot is still one person's sleep time. So they represent the same thing. It's just that here we're looking at a subset of the population, just these 30 people that have been selected. We also have numerical values to summarize the sample. These aren't called parameters, these are called statistics. In the third graph, we're taking the sample mean that we got from this one sample, so like here we have 8.1, and we're plotting that sample mean. So let's do it again. Let's take another random sample of size 30. This time the mean was 7.283, and you can see that value showing up on the plot. So every sample you take, you're getting different values from the population, so you get a slightly different mean, and we're plotting the sample mean each time. So basically what this is showing is if you take a sample of size 30, what are all the possible values that you can get? So I'm going to change the number of samples here so that I have a whole bunch. This will bring me up to 10,000. Take just a second. So this third plot over here, this is called the sampling distribution. So we saw sampling distribution before in terms of proportions. This is the sampling distribution in terms of means. But the key thing about a sampling distribution is that instead of representing individuals, each dot is a statistic. So in this case, every dot represents a sample mean from a different sample of size 30. Remember, the standard deviation of a sampling distribution, that value has a special name. This is called the standard error. So the standard error is the standard deviation, but it's a sampling distribution instead of a regular distribution. And when we interpret, we have to just make sure that we're acknowledging that the values are actually sample means. So we would say on average, a sample mean, that's what our dots represent, is 0.277 from the mean, which in this case is 8. So that value is the true population mean. So we have our sampling distribution centered at the true parameter. So if we think about trying to use a sample mean to estimate the population mean, this is telling us how far off we'd expect to be. So this seems like a silly exercise where we're pretending we know what the population is, which is something that would never actually happen. But this statement that we've written, you can imagine how it would be very useful in reverse, right? What if we only had the sample mean? Then knowing how far it would be from the true population mean would be really helpful information. You'll also notice that the sampling distribution has that nice bell shape like we saw in the dice example. And later on, we're going to learn how to use theory to model the sampling distribution instead of using a simulation. Sampling distributions tend to be really difficult conceptually, so I wanted to give you some time here to stop and try to make sense of the sampling distribution. So go ahead and do your best to try to answer these 3 questions. I would recommend writing your answers down, commit to them, and then I'll come back and discuss the answers. So the first question is, why is the spread of the sampling distribution so much smaller? And I think the easiest way to think of this is, why do we not have values of 4 or 12 in the sampling distribution? So if you notice, values of 4 and 12, those are way out in this distribution. And remember, here, each dot is a sample mean. So to get a sample mean of 4 or 12, you would have to randomly select 30 people, and all of them would have to be in that tiny little tail of the distribution down by 4 or up by 12. So even though it's possible to have an individual person who's only getting 4 hours of sleep or 12 hours of sleep, it would be very, very unusual to take a sample of size 30 and end up with a mean of 4 or a mean of 12. In fact, as sample means go, it looks like maybe 7 and 9 are about as extreme as it gets. So to summarize, sample means are much less variable than individuals. Much less variable than individuals. So you may have individuals who are only getting 4 hours of sleep or 12 hours of sleep, but it would be very unusual to take a sample of size 30 and have everybody at those extremes. It's much more likely that you get some that are high and some that are low, and it kind of balances itself out. So you end up with sample means that are much closer to the center. So then how does the spread of the sampling distribution change as the sample size gets larger? This is really just an extension of the earlier question. So if you think about this tendency for things to eventually balance themselves out, that's going to be even more true with a larger sample size. So let's compare. Here with a sample size of size 30, we're seeing means all the way from like 7 up to 9 almost. What if we take samples of size 100? So now it looks like the distributions really only go from like 7.5 to 8.5. So at this point, the statistics are even more precise estimates of the parameter. So to summarize, as the sample size goes up, the standard error goes down. And finally, which sample would provide the strongest evidence that people don't get enough sleep? So there's 2 things to think about here. One is what the sample mean is. So if we're trying to prove that people don't get enough sleep, then values further away from 8 hours are going to be stronger evidence. So it has to be one of these on the left. Then what about the sample size? So we said that the larger your sample size is, the smaller your standard error, meaning your estimates are more precise. So here, not only do we have a sample mean that's really far away from 8 hours, but also we have a more precise estimate. So this is more reliable. So the 2 things that we're looking for here is that the sample mean is further away from 8. So if we're trying to prove that they get less than 8 hours of sleep, further from 8 is going to be stronger evidence, and also that this one has a larger sample size, which is good because that means that we have a smaller standard error. So those 2 things together give us the strongest evidence.